different kernel stacks, and you core dump one of them, and in this core dump, it will actually have your task structure from the kernel, and you can look at its parent and sibling pointers, and if you see that they're right next to yours, or right next to each other, then you know they're right. Then you know that there's something. You know exactly where they are and that they're right next to each other, right? So that means that you can now have one right into the stack of the other. And what's interesting in Linux is that kernel stacks are right after your task structure. They're right next to each other, right? There's no paging between. So this means if you would have a recursive stack overflow in the Linux kernel, eventually you end up overriding somebody else's or your own task structure. And so in your task structure, it contains things like your UID and your saved UID and your groups and effective UID and all of these things, right? So if you have these kind of things, you all of a sudden get to change your UIDs to whatever you want them. So that's kind of bad. That was recursive stack overflow. The next one will be shifting the stack pointer, where I get to bitch on the C standard and alloc-A. Basically, if you want to dynamically allocate any kind of array on the stack, there's sort of two ways to do it. So the first one is I guess it's called in C99 standard, dynamically allocating arrays on the stack, and this is basically how you do it, right? You have to function with the length, and you just declare it like this, right? And I think this, is for C it's kind of weird because you usually don't do this kind of thing, but the C99 standard allows for it, and so this sometimes works, and I'll tell you why later. And then the second one, which basically does pretty similar things, is alloc-A, and it's sort of. And the cool thing about alloc-A is that it looks like it's malloc, but you never have to free because that happens automatically, right? The problem with alloc-A is that it's really difficult to actually implement it right. And the actual alloc-A man page says this and says, well, you really shouldn't use alloc-A because it's compiler and machine dependent and probably even operating system dependent, and it's really buggy on most systems. It's use discouraged. And what they really mean is it's really buggy on almost all systems. And I'll tell you why in the next couple of slides. So this is basically how you use these functions, right? They're pretty straightforward to use. That's how it works, right? So the problem basically becomes is what really happens if you do these things is basically you just locate more space on the stack, and what this really means is that all you have to do is sort of modify the stack pointer, right? Because that basically gives you some piece of memory on the stack. And that's what your compiler does. It generates code that does nothing else but basically just subtract an arbitrary amount of length from the stack pointer. And the code generated for alloc-A and these C99 dynamically allocated arrays on the stack are identical. They do the exact same thing, right? To the exact, and it's only 4 or 5 instructions, and they're exactly the same instructions. No error checking is done. What that means is, if you have an unbounded alloc-A call, you have full control over the stack pointer. And that is really bad. That means you're owned, right? If they're not unbounded, so if they're bounded, it can still be problematic because they might be very long strings, right? If it's something on your control and they use the length of a string or something, it might still be bad because it might not fit on the stack anymore, right? It would just modify the stack pointer without checking for stack overflow. So you sort of end up in the problem that I just talked about, even if it's not unbounded, but it's really big. Things, problems might still occur, right? You might get stack overflow. So depending on what context you're in, these kind of things might still be exploitable or might not. I don't know. And so I went looking for a piece of code that, gives you these things, and this thing comes out of the Linux kernel. This is a right hook, and so the counting used there is basically, the value you give to write. And up until not too long ago, that was totally unbounded. And now it's sort of bounded. It can be up to 2 gigabytes, so up to like 2 billion something. So it's sort of bounded, but it's not bounded enough. This thing's exploitable. This is really problematic. Well, it should be, but this is PA risk specific code. So there's maybe 2 or 3 people in the world affected by this. So yeah, so basically the problem is compilers are just, so alloc A is basically an inline function, right? So it's not really calls anything, it just adds the assembly code in there. So the code for allocating dynamic size arrays on the stack are identical, and compilers they put very dumb code in there, it doesn't check for anything. And so I've tried this with GCC, and I've used the Sun compiler and the Intel compiler, and they all do the exact same thing. It's 4 or 5 instructions, they just modify the stack pointer without doing anything. Here's the shocking thing, Microsoft does it right. Hey, you know, they've invested all of this time and resources in security, and it's paying off. So with alloc A, what they do is, if you give it some length, they probe every page. So it's slower than what you would do in GC stuff, but it buys you stability, because they probe every page, and the moment they find a page that's not mapped, basically they just throw an exception and say, you know, this thing blew up, handle it correctly. And of course that's the cool thing with Microsoft's Visual Studio, is that it's not really C or C++, it's their own mix, and that means you can have C with exceptions or C++ without exceptions, or whatever kind of strange mix you want. But it works out for alloc A because it can just throw exceptions. And what's even better is they don't implement C99 dynamically sized arrays, because honestly it's a horrible idea. So, and I bet, you know, somebody at the Microsoft compiler group, they read C99 spec and he's, you know, oh, there's dynamically sized arrays on the stack. They must have been smoking crack when they wrote this, right? So they don't implement this, and because you don't really need this stuff, right? Look, if you want to dynamically allocate memory, use the heap, right? And the punishment you get is that you have to call free. That's your punishment for wanting to have dynamically sized arrays of any kind, right? So just use the heap. They're meant to do these kind of things. The stack is not. Right, so that was shifting the stack pointer. Next thing I'll talk about are reference counting issues. And so basically I found this other quote from somebody in Mozilla who realized the exact same thing. I'm not going to read it again because it's way too long. But if you happen to run the slides later, this pretty much explains the entire thing. So basically, reference counting is sort of a way of memory bookkeeping. And so it's or at least it seems like it's an easy way of memory bookkeeping. So what basically happens is you can have certain objects, in memory, and people would reference count them. And you do this so that you prevent freeing objects while you're still using them. So what basically happens is, if you have some kind of function which takes this object and uses it, it increases its reference counter. And then when it's done using it, it decreases it. And when this object's reference counter gets to 0, it gets freed, because that means nobody is using the stuff anymore, and it's safe to free it. Well, this sounds easy and easy to do. Turns out it's actually not, because you sort of have to, for every case where you use an object, you have to basically do 2 calls, which is increase reference counter and decrease it. And it turns out that in specific error cases, it's really difficult to keep these things balanced. Well, apparently it's difficult because everybody keeps making these mistakes. So one of the most common mistakes that people make is they use the object and they increase the reference counter, but in some error code paths, they forget to decrease it. So what this means is the reference counter, before you got the object, it might have been 1, and then you use it, so you say +2. And then you forget to unuse it, right? You get to say that you don't want this stuff anymore. So the reference counter stays at 2. And then the next time you call this particular code path, the exact same thing happens. The reference counter goes to 3, and it goes to 4. And it goes all the way up to the maximum limit of whatever integer this reference counter is. If it was an integer, it would be 0x, ffffff. And then the next time you call this thing, it increases it again, and oh look, you get an integer overflow. It starts counting back from 0 and goes to 1 and 2 and so forth. So it's sort of a special case of integer overflow. And so I've sort of made a demonstration for this because I hope this makes it clear. So this, what basically happens is, you would have something, let's say an object, in this case a file structure, right? So you open a file and you duplicate it. And what usually happens in most Unix implementations is if you duplicate a file descriptor, you still end up with only this one file structure in the kernel, but a reference counter goes up. And this is to save memory, right? Because if you would actually really duplicate memory blocks for every time you do a file duplicate in userland, you end up wasting a lot of memory that you really don't want to, right? So the reference counter goes to 2, and then you call some function or some system call. And in this case, I've called it ref counter overflow because kind of makes it easier to demonstrate this thing, where you call this thing and it increases the reference counter. And then it forgets to decrease it and does it again and again and again. It goes from 1 to 2, 3, 4, 5. The maximum limit, excuse me. So the maximum limit goes back to 0, goes back to 1, stops. So what you end up with is you still have 2 file descriptors pointing to the same file structure, but the reference count is off. It's wrong. It should have been 2 and it's actually 1. So what this means is so you now close one of them. So normally, so what this means is the reference count gets decreased by the close. And these memory functions, these memory bookkeeping functions go like, oh look, your reference count is 0, I get to free this object. Unfortunately, you still have one reference to what used to be your file structure in, well, it's now free memory. So you sort of, with these kind of bugs, you end up sort of being able to read or write to free memory, or memory that's supposed to be free, and that's usually really bad. Right. So I have another example of this stuff. This is from NetBSD. This is sysfsync range. I have no idea what this thing does, but I do know that it has a reference counter issue in it. And so what really happens is, so they call this thing called getVnode. And it gives you the file structure of a file descriptor given as an argument to the system call. And vnode basically says, oh, I want this file structure, which is sort of an object, right? And because I want it, I'll increase the reference count. So they basically, getVnode internally calls this thing called file use. And then, the file descriptor set instead of 1 to 2, for example, and then, some non-interesting stuff happens. And then they check this thing called flags, which you have full control over. And they're like, well, if it's not exactly the way I want it to, let's just bail out and not do what you want it to do. And so they basically return from the system call without decreasing the reference counter. Decreasing reference counter is basically where you use file unuse. So if you would call this particular system call 4 billion times and then somewhat, the reference counter goes to 0x FFFFF, and next time you call it, it goes to 0. And then it might go to 1 again, and 2, and so forth. So, but the thing is, you probably want it to be at 1, because the next time you would, you then have, as seen here, you'd have a duplicate copy, you'd close one, and you'd end up pointing to free memory. Right. So this sort of issue has sort of an evil twin. Where instead of forgetting to decrease reference counter, you decrease it twice. And these kind of bugs are pretty rare. They're usually in horribly ugly code paths where you have, go to, error out, and then you go to something else went wrong and go to something else, and then nobody can really follow all these go-tos, and you end up with, for example, double decreases. They're somewhat easier to exploit because you don't really have to sit around and wait for ages, right? Because in the previous case, if you have to wait for reference counter to overflow, it takes like hours or it might even take days, right? So, but you don't really want that, right? Because it takes ages, right? I mean, who wants to sit around and look at a screen for 10 hours in order to get a root shell, right? So with the evil twin here, you don't have to do this. It's instantaneous, right? Because a double decrease in the reference counter this basically means that the reference counter should have been higher than it should have been higher, but is not. So you could just free something and still have references to it. right? So this kind of thing is really bad. The exploit can be instantly, right?